Hello, good evening, everyone. Today we are practicing a 15-degree formula equation using Ezouidi theorem. So, in fact, this theorem is a method that bypasses Abel-Rafini limitations by exploiting structural factorization. Let's dive into the polynomial and its exact roots. Okay, so this is the polynomial. This is the polynomial. I will show now. Okay. Again, we call that welcome to this exciting live stream session. I'm Professor Murat Sultan, and today we are going to tackle one of the most challenging mathematical problems, solving a 13-degree polynomial, something that traditional methods simply can't handle. We will see how my method, the Ezouidi theorem, allows us to find exact symbolic solution where others fail. Let's dive into this problem to the power 13. Now, I will share the screen with you, my professors, learners, and students and colleagues, so that you can see that symbolic exact roots, in fact, are reachable. Okay, so this is our 12-degree from the equation. These are the coefficients. L0 is going to be equal to 13, L1 is 78, L2 is going to be equal to 286, L715, L4 is 1287, L5 is equal to 1716. Also, this one has to be equal to 1716. L7 is 1300, L8 is equal to 780, L9 is equal to 416, L10 is 208, L11 is 91, and L12 is going to be 27. Here in this example, 13-degree from the equation, you will see that, uh, yes, yes, okay, yes, I'm looking to, yes, I'm here, Samia, okay. So here we call that we will put the coefficient of this order 13-degree from the equation, and we will write in its standard form, that is x raised to the power 13 minus L0 of 42 x raised to the power 12 plus L1 of 42 x raised to the power 11 minus L2 of the q x raised to the power 10 up to negative L12 of 42. This is negative L12 of 42, and this one is negative 27. You see, means that 12 is going to be equal to 27 because I have same sign. So that's why here certain 27. Okay. So here I'll just answer one volunteer who's asking. Okay. So here we call that professors, teachers, and colleagues. Here, in fact, here is the formula we are solving today. As you can see, is a 13-degree polynomial equation. Traditional method would rely on numerical approximation, but we are going to approach it systematically using my theorem. First, let me point out something. Okay, when here x is going to be equal to 1 is a root is a root of multiplicity 5. Okay. And the other roots has to be equal to 1 plus 13 raised to the power 9 over 8 exponential 2k plus 1 I5 divided by 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 8. Okay. So here, in fact, this explanation, my professors and teachers and colleagues, you will see that. Okay. In fact, we thought that this explanation should provide a solid understanding of the challenges classical method face when solving high-degree polynomial equations, and how Murat Sultan's Ezouidi theorem offers a promising alternative. My method here, my professors, teachers, and my colleagues, based on my theory, excluded all classical methods, including includes, including Abel's theory, which says that certain polynomials can't be solved using radical. Contrary to Abel's assertion, My method demonstrates that even polynomial with radical roots can be solved exactly. When traditional approaches fail, my theorem reveals the exact symbolic roots through a structured process that bypass the limitation of classical algebra and numerical methods. This is not just a numerical approximations, but it provides precise solvable roots of problems that would otherwise be deemed unsolvable. Okay, so here, professors, it's an occasion for you, my colleagues, to understand this, the concept of this theory, okay, that bypass abelian assertion and abelian limitation in algebra. So here you can see that I will apply the theorem of Murad Sultan's video. Okay, this is the theorem is written as S subscript k minus 1 of 42 equals the sum from 0 to k combination n minus r plus k minus r n raised to the power r between parentheses negative at 0.2 raised to the power k minus r times L r minus 1 of 42. So here you can see that this is the formula. So here is the formula that we will use to compute the roots. Let's break it down. You see combination n minus r to k minus r. These are binomial coefficients that adjust the terms. N raised to the power r, this term raises the degree of the polynomial. And this one, you see negative L0.2 raised to the power k minus r. This involves the base coefficient L0.2 adjusted by the power k minus r. And LR minus LR of order r minus 1, which is of course r minus 1, okay, is denotes or refers to the area terms in the polynomial as we proceed through the recursion. So here, professors, we should, let's say, find the value of sk minus 1. Okay, so this is the polynomial p of x equal a coefficient L0 is 13, L1 is 78, up to L12 is 27. Now, professors and teachers and colleagues and learners, Ezouidi theorem. See how Ezouidi theorem works. Theorem statement. For polynomial structured with recursive coefficient constants sk minus 1 of order 2 equal the sum from 0 to k combination n minus r choose k minus r n raised to the power r between parentheses negative L0 42 raised to the power k minus r times n r minus 1. This will give you, in fact, the coefficient of the new 13-degree from the equation. After that, finding the coefficient of this new 13-degree from the equation, solve for x. And after finding the x values or the exact x roots of this new 13-degree from the equation, go back to formulate alpha subscript k equal L0 plus xk divided by 13. Here the polynomial factors into solvable components, enabling exact sample roots when most sk minus 1 here in this example tends to 0 or is going to be equal to 0 except critical terms as 7 of order r which is equal to 13 raised to the power 9. Okay. So let's see the key concepts here about constraints. Here we have S0 is equal to S1 is equal to S11, which is r equal to 0, except S7 order r is 13 raised to the power 9. Now I'm going to write my new polynomial to the power 13 as p of x equal. You see, it can be factored. We can factorize this polynomial when S0 equal S11 equal 0 except S7. So retain x to the power 5 times between parentheses x to the power 8 plus 13 to the power 9 equals 0. So here, exact here assembly proofs x raised to the power 5 is going to be to 0, means that x equals 0 the multiplicity factor. From x raised to the power 8 plus 13 raised to the power 9 equals 0. Therefore, I will write xk equals 13 raised to the power 9 over 8 exponential 2k plus 1 times pi divided by 8. Okay? Of course, k belongs to the set of numbers from 0 to 7. After finding here the k, I will transform those. Going back to transform it, we have The exact roots of by 13 degree polynomial equation is 13 plus xk divided by 13. So 13 divided by 13 is what? And you see here 13 divided in 13 raised to the power 9 over 8 divided by 13 will give you exactly 13 raised to the power minus 7 over 8. Exponential 2k plus 1 I 5 divided by 8. So here the roots, the exact roots of my 13 degree polynomial equation. This one, okay? This one is the polynomial to the power 18, this polynomial, you see, to the power 13. These are the exact roots. And in fact, we applied the theorem of Murat-Sultan Ezouidi, and we obtained that as 0 is going to be equal to 0, and we extend our formula to find S1. This is the value of S1 here is going to be equal to NO. Also here, S2, my professor is going to be equal to NO, okay? And we continue the process. Here we find S3. This is in S3. My professor teacher, colleagues, and numerical researcher. This is S3 is going to be equal to NO to 0 means we continue. We found that the value of S4, I should put K equal 5 as this kind of formula, and I should calculate S4 here. S4 between parentheses is going to be equal to NO multiplied by 13 raised to the power 5. So it's NO means that this S4 is 0 modulus 13. Okay, so here also we can see that when K equals 6, I will use this formula and I will replace LK and R minus 1 with their values, and I will obtain that the value of S5 here is going to be equal to NO. We continue the process and we want to find, let's say, S6. Okay, S6 here is equal to 0. I will apply this formula when expanding the theorem of Murat-Sultan Ezouidi. You will just make substitution and do your best to demonstrate that it is equal to NO. Look here, when K equals 7, we will get, let's say, the S7 different value. Okay, so this is S7. 7 here is going to be equal to 13 raised to the power 9. Because 13 raised to the power 8 is a common factor. Okay, you can factorize it. I will make it as a factor. So I will factor it out, sorry. So I will remain with 13. Okay, so 13 raised to the power 8 times 13 is going to be 13 raised to the power 9. Means the total of this is 13 raised to the power 9. So a 7 here is going to be different to you. When K equals 9, I will obtain the 9th coefficient. I will use this formula and I will substitute to get that S9, S8 here is going to be equal to 0. We continue to find the S10. To find the S9, put K equal 10 in my theorem. This is my theorem. Okay, and we obtain that in fact the value of S9 here. S9 here is going to be equal to just calculation. You can use the calculator and calculate. Now the question is that, okay, the question is that K equal 11, I want to find S10. S10, I will extend, or I will put K equal 11 in the formula. I will obtain S10 equal. After writing the formula in its lowest term, I will now make substitution. And then I'm going to calculate S10. S10 here is going to be equal to 0. Before the last steps, we have remaining only 2 steps. I will put K equal 12 in the theorem combined. Then I'm going to write S11 is equal to, okay, this is S11, this is S10, this is S11. I will use this formula to calculate S11 by professors. Okay, this is general formula for any degree polynomial equation, and we obtain that here is equal to NO. Okay, now by noticing something that 13 raised to the power 12 is a common factor. Just make the total of the combination of the binomial coefficient and the coefficient of the original 13 degree polynomial equation. So here we found that S11 is equal to 0. Now let's find S12, the last coefficient of my new 13 degree polynomial equation. Just set K equal 13 as by theorem, and you will use the last formula, this one, after writing it in its lowest term, and make substitution, and you find that the value of this here is going to be equal to 1. So this is in fact my original polynomial to the power 13, I will obtain another polynomial to the power 13, but written in terms of sk minus 1 for that. In other words, S0 equal is 0, S1 is equal to 0, S2, S3, S5, S4, S6, S5, okay, S8, S9, and S7, S11 are equal to 0, except S7 is different to 0. Now, in like, let's say, traditional methods, which often use numerical approximation, here, Ezouidi theorem provides precise symbolic roots. This ensures that the roots we obtain are exact and not subject to the errors that arise with numerical method. So here, our polynomial to the power 13, which is new, that corresponds to the original 13-degree polynomial equation, can be written as x to the power 13 minus s0 or the r x to the power 12 up to negative s12 for the r equals 0. You see, this polynomial to the power 13 had been written as x to the power 13, was 13, okay, plus s7 x times x to the power 4, okay, to the power. Okay, this is 30, 12, 11, 10, 9, 8, 7, 6, 5. Okay, so 5, yes, x to the power 5 equals 0. So here, x to the power 5 equals 0, or x to the power 9 plus 13 raised uh, to the power 9 equals 0. Means that x equals negative 13 raised to the power 9 exponential to k plus 1 I pi. Now I'm looking for xk. Xk is equal to 13 raised to the power 9 all raised to the power 1 over 8. Okay? Exponential to k plus 1 I pi divided by 8. This is divided by 8, not 9. Okay? And this is 8 because the highest power here is going to be equal to 8 x3. So now, my professors, we found the axioms of this Newton equation. What's needed now is just go back and write alpha subscript k equal between parentheses 0.2 plus xk all divided by n is going to be equal to 13 means divided by 13. So the roots are derived recursively, where we solve for them step by step. This formula break down the polynomial into manageable components, allowing us to derive exact symbolic values instead of approximations. Let's see how it is. So here you see the alpha subscript k from 0 to 7. Okay, 9, yes, to 7, this one is to 7, is equal to 0, 42 plus xk from 0 to 7. Will be 13 plus this one, plus 13 raised to the power 9 all raised to the power 1 over 8, multiply by exponential, 2k plus 1 I pi divided by 8. Okay, so this one has to be written 1. 13 divided by 13 is 1. Okay, and 13, uh, 13 raised to the power, I can write 9 divided by 8. Okay, 9 divided by 8. But I will write it as exponential 13 raised to the power 9 all raised to the power of 8 exponential to k plus 1 divided by 8. Okay. Divided by 8. So these are the symbol roots. Or alpha subscript k from 0, 1 to 4 is at 0 plus x k from 0, 1 to 4 because 5 roots 2 to 4 is equal to, we told x raised to the power 5 is going to be equal to 0. You see this one? That's why he would put 0. So 13 divided by 13 is the root of multiplicity 5. Okay. As here, we told that uh, alpha subscript k to 13 plus xk divided by 13. These are the correct roots. Now, if we are going to make verification of making checking, substitute x equal 13 raised to the power 9 divided by 8 exponential pi I divided by 8 into p of x. So this one has to be written as that p of x equals 13 raised to the power 9 divided by 8 exponential pi I divided by 8 raised to the power 13 plus 13 raised to the power 9 times 13 raised to the power 9 over 8 exponential by I over 8 all raised to the power 5. Why? Simply because this is the expression of the this one. I could just substitute x with the value. I will use this one. That's why you see this here down. Okay. And here we'll substitute we call the x equal that in p of x, and we should find p of x has to be equal to 0. You see 13 raised to the power 9 over 8 times raised to the power 13 will give you 13 raised to the power 117 divided by 8. Okay? And 13 pi divided by 8 is going to be equal to negative 5 pi divided by 8. The next term, we see 13 raised to the power 9 times 13 raised to the power 9 over 8 raised to the power 5. It will give you exactly 45 plus 72 will give you 170 divided by 8 plus exponential 5 pi I divided by 8. You see this one? This is different in the order. But this one is equal in fact to another. Exact cancellation confirms validity. Exact cancellation confirms validity. This is the property I'm going to read. Here we will address to Abel-Rafini. First, Abel-Rafini applies to generic polynomials, but Ezouidi theorem targets abstracted ones. By designing polynomials with recursive coefficient constants, we bypass a possibility. If learners and professors want to make comparison to numerical method, even Abel's theorem, we'll see that the Murad Sultan Ezouidi theorem bypass the limitation of algebra, and he redefined and he redefines uh, uh, new limit, let's say redefines the limits of algebra. Okay, so here the comparison. This is the aspect, root type, applicability, and transparency. For the theorem of Murad Sultan Ezouidi and numerical method, we compare one by one. For root type, exact symbolic roots. For numerical method, approximation with errors. For Ezouidi theorem, applicability, structured polynomials. For numerical method, generic polynomials. Transparency, algebraic factorization, okay, iterative black box algorithms. Okay, here we can say that congratulations to Ezouidi theorem. Today we have shown that structured polynomials defy traditional limits, offering exact solution when others see a possibility. This is not just math, it's a leap towards precision in science and engineering. So Ezouidi theorem, exact roots for structured polynomials with social and distinctive for wrestling. Okay, so this is the problem that we solved, and I want to say something before leaving. For okay, just a moment. Here we told that unlike traditional methods, which often use numerical approximation, here Ezouidi theorem provides precise sample solution. This ensures that the roots we obtain here in this example are exact and not subject to the errors that arise with numerical methods. Now, now that we have calculated the exact sample roots, let's verify that. Unlike traditional numerical method, which can introduce rounding errors, these roots are exact. Let's substitute them back in the original equation to prove that satisfy the polynomial perfectly. Here I will use the verification process. I will show you how to substitute each root into the polynomial p of x and display the confirmation that p of x is symbolic verification tools live to do this. Okay, so I will come here. I will come here. I will share this so that we can check with the professor. Murat Sultan Ezouidi. Okay, we told that x equal 1 is a root multiplicity 5, isn't it? Okay. And the other complex roots are already verified using the new 13-degree from the equation. Okay, so here, professors, this is the polynomial to the power 13. I will consider this one. I will make like that. Okay, copy, and I'll come here. Okay, I'll come here. I'll come here. Today. Okay, I will erase this limit. Okay, control V. Here I'm going to change what? X with 1. Because we told that x is going to be 1. So 1 raised to the power 13 minus, okay, 13. Okay, raised to the power 13 times 1 raised to the power 12 plus 78 times 1. Okay, raised to the power, I will just make this copy. I need it. Okay, good. Then minus 268. Okay, times 1 raised to the power 12 plus 715 multiplied by 1 raised to the power 9 minus 1278 multiplied by 1 raised to the power 8 plus 1716 multiplied by 1 raised to the power 7 minus 716 times 1 raised to the power 6 plus, of course, I will write 1 plus 1300 multiplied by 1 raised to the power 5. Okay. Then minus 781 raised to the power 4 plus 416 multiplied by 1 raised to the power 1 minus 208 multiplied by 1 squared plus, okay, plus 91 multiplied by 1 minus 27. Mean is here, I will just add the coefficient. I will use the calculator and will verify this in fact is equal to a no. Okay, and mean is this 13-degree from the equation only by the method of Murat Sultan Ezouidi can do. Even AI, artificial intelligence, they are unable to solve this polynomial without my guidance. Okay, and also I will show the example for DeepSeek. First of all, he told that it's impossible to solve this polynomial, but I gave him the steps. So I trained him, and at the end he told me your theorem 100% correct. Okay, so here I will use it called the calculator. I will write exactly this is 1 minus 13 plus 78 minus 286 and so on. So I'll make 1 minus 13 plus 78 minus 286 plus 1716 minus 1716 plus okay 715 we didn't 715 we didn't make 700 okay plus 715 this one we need then minus 1200 yes minus 1287 then plus 1300 minus 780 plus 416 minus 208 plus 91 minus 27. So this one, professors and colleagues and numerical researcher is equal to 0. You see? Meaning that we already proved the 13-degree from equation is solvable, okay, and this bypass the limitation or Abel's theorem or Abel's assertion or Abel's limitation, okay? So, thank you for listening, okay? This is Murat Ezouidi was with you, okay, live, so that to let you practice this theorem and to get ready to understand the deep research, a deep uh, research in the field of solving or mastering the solution of a degree polynomial equation. Okay, thank you for listening and see you inshallah next time. And, okay, just a moment. I will show you something before this moment. Sorry again. So this is we called our polynomial to the power 13. I will make verification. I forget to share the screen. So this is you see this one we called 1 minus 13 plus 78. 1 minus 13 plus 78 minus 287. Then plus 715 minus 1287 plus 116 minus 116 plus 100, 1300 plus 1300 here in the calculator minus 780 plus 416 minus 208 plus 91 minus 27 minus 27 is equal to 0 and here equal to 0. Okay, I will look at this for you. So we have 1, this one we start from here, 1 minus 13 plus 78 minus 286 plus 715 minus 1287 plus 1716 minus or plus minus okay minus 1716 plus 1716 we finish this one okay plus minus okay so then plus 1300 minus 780 plus 460 minus 208 plus 91 minus 27. This one, my professors, has to be, what is the equal sign? Yes, it has to be equal to an hour. And here we make our verification process and we show by substituting each root in the community of x and we find that we do path equal to an hour. Okay, thank you for your for watching the lecture and I hope so that you got the point. Okay, okay. Here you can see that. Okay, this is the other verification process when x equals 13 raised to the power 9 over 8, so if by over 8, we put here and we find that is coefficient different to 0 times now is equal to 0. Thank you. And this one is in fact exact cancellation confirms validity. Thank you and goodbye. See you next time. This is the professor. Lots of video was with you. Goodbye. See you inshallah. See you my professor that is learning English here from Muslim. Kalala from second government I was flying so that to let you understand that here we can apply a new approach, new theorem that will help you to find solve 13-degree from equation when in the past was insoluble or was impossible, but now we close this door and we open another door and we take it forward to say goodbye. See you.